I have here some metal. Now, one of the things about metal is that it'll respond to force. In fact, if I apply a force to this, this becomes elongated or longer. It increases its length. I can extend it. Now, what we're going to do in this little demonstration is look at the relationship between a force that's applied to this metal and how much it gets longer or it's extended. So to begin with, I'm going to start with 50 grams hanging from this and add 50 grams each time and see just how much longer it gets. Now, to begin this, what I need to do is find out its original length, because what I'm interested in is not so much how long it is or how big it is, but the extension. So looking at that at the moment, when I read that, that is 17.5 centimetres, otherwise known as 0.175, which I'll write down. So that's with no mass added. So putting now the 50 grams, and that means a force of 0.5 kilograms weight, multiply 0.05 by 9.8, that will give me the force in newtons. Okay, so I can record that in the table. Now, measuring this length here, that length there is 28.5 centimetres. In other words, 0.85 metres. Adding another 50 grams, giving me a total of 100 grams, otherwise known as 0.1 kilogram. Multiply that by 9.8 to get the force in newtons. So, measuring that length, that's 40. So 0.4 meters. Adding another 50 grams, that's a total mass then of 0.150 kilograms. Multiply that by 9.8 to get the force in newtons. Measuring the length, that's 51.3 centimetres, otherwise known as 0.513 metres. Adding another 50 grams, that gives me a total now of 200 grams. And looking at the extension, oh sorry, not the extension, the length. Trying to avoid a parallax error, that's 63 centimetres or 0.63 metres. And our final measure This time it's 250 grams, and otherwise known, of course, as 0.25 kilograms. Multiplying that by 9.8 to get the force. And looking now at the length. That's 74 centimetres. So now we can work out a couple of things. First of all, the force for all of those extensions, and then the extension. Now what's needed in order to work out the extension, of course, is a little bit of subtraction. We've got to subtract the 0.0175 from each of those numbers, each of those other measures of the length. So that that'll enable us to work out then the extension. So with that done, what we'll be able to do is put that into a spreadsheet and graph the two values against each other and see whether or not we get a straight line, and what does that straight line represent. So I've got the spreadsheet open now, and I've recorded or put in some of the data. I'll just tidy up the width of the columns and the decimal places. So I'll give each of these ones here 3 decimal places. So I'll go up to the top here and click this one, and then back to that one, so 3 decimal places, and this one here to 2 decimal places. So click in that, and then click in that one. The force we can calculate by using a formula. In this particular case, what I'm going to do is put in here V2, this cell here, times 9.8, and I've just filled that down, so that does all the calculations for me. Now I'm going to use a formula to do the subtraction here, and in this particular case I'll type equals, and we're going to take this cell here and subtract the value of A2, and that'll give us a number of 0. But what I'm going to do is subtract this number, the value that's in A2, the original length, by subtract that number from each of these other numbers. So I'm going to make this what's called an absolute cell address by putting dollar signs in front. So what those dollar signs mean is don't change these letters and numbers when they are copied into another cell. So if I press enter, I'll get that figure. The extension then is 0, and if I fill down, I'll get then the values of the extension, just how much longer the spring was as a result of adding the additional force. So I'll just make this into a table. So by clicking that and then going up here and selecting the format of the cell. And so now we're in a position to generate the graph. So I'll select these numbers and go up here to insert, across here to charts, and select this one and move it so that we can see the other bits of the table and so on. And we can add the chart elements such as the axis title. I'm going to call this Hooke's law, and I'll put in the chart, the axis titles, And the other thing, of course, is to put an equation on the chart. So I'll select the plus sign here, go across here to trend line, mark that in, and go down here to more options. And from more options, select the display equation on the chart. And I might also set the intercept to 0. Now, that's certainly a justifiable point. It is one that we've got written over here. And the thing about it, of course, is that with no mass or no force, then we've got no extension. So there we have the gradient, y being equal to 0.24. So I'll just reduce that a little bit now. That is the reciprocal of the spring constant. The idea of a spring constant was derived by Robert Hooke. Now, Hooke was also famous for discovering cells, the first discoverer of biological cells. So in this particular case, the value for our spring constant is going to be equal to 1 divided by 0.24. In other words, 4.35, let's say. And the units for that, of course, will be newtons per metre. Different springs or different pieces of metal, of course, will have different values for the spring constant. These spring constants are used then in engineering for working out just how strong a spring has to be.